Welcome physical science students as well as Physics 100 students. This is your waves and velocity of a sound lab. Okay, I'm going to start with some preliminaries. Sound is a wave. If the frequency of this wave is between 20 and 20,000 cycles per second, we call it sound. Higher frequency we call ultrasound, which some of you are interested in. Lower frequencies we call subsonic. Now, why do we call sound a mechanical wave? Picture this. You're in a bird's eye or a drone view of the ocean, and you have perfectly symmetrical waves, and you look down. This is what you're going to see if you were to plot it. If you plotted the disturbance of the waves, the peak and the trough amplitude, as a function of the distance, you'd see a pattern where the waves go up and down, but they repeat themselves. The distance which they repeat themselves is lambda, that thing that looks like a giraffe there. I lost my pointer. Just a second. No, not a second. All right, I'll do without it. Now, if you ever sat on a dock or on a lake or in the ocean, you're floating around, and a wave comes by. The water starts at rest. We look at the second picture. It goes up, reaches a max, goes neutral, goes down, goes up. It doesn't appear to be waving, just going up and down. But if you plot the disturbance of the amplitude as a function of time, it's got erased, you'll see the same graphic picture, that it repeats itself, it cycles. And the time to complete one cyclical motion from maximum peak to maximum trough, back to maximum peak, is called the period, capital T. It's seconds per one cycle. Well, the frequency is the inverse of the period, 1 over t. That's cycles per second. And we're going to be using hertz. But they're the same thing. Your electrical grid is 60 cycles per second in the USA. All right, now, the speed of anything, or the velocity, if it's constant, is the distance traveled, d, divided by the time it takes, little t. The distance traveled during one repetitive cycle is called the wavelength, that thing that looks like a giraffe. The time to complete that cycle, on the right in red, is the period. So the speed of any wave is wavelength over period. But since period is 1 over frequency, we get our final expression that we'll be using. That the speed or velocity of waves is the frequency of the waves times the wavelength. We move on over. Now, the property of a mechanical wave, such as a sound wave in air, also depend on the mechanical properties of the mechanical medium in which they propagate. In general, cutting off the camera, the velocity of the mechanical waves depend on two properties: their stiffness, elasticity, or compressibility. How easy it is when you put a force or pressure on them for them to stretch out or compress. Also something called the density, the inertia. The more stuff there is concentrated, the more molecules you got to rock back and forth when the disturbance of the wave propagates, it's going to slow it down. It provides resistance. But the stiffer the medium is, the more it's going to jump. You pull a steel cable across the room and you pluck it, the waves go crazy. You take a limp, nylon cord for you put your laundry up, it's slower. Anyone who's ever dropped metal on a hard cement floor knows that those waves go quickly. That sound is loud and fast. And so the speed of any wave, mechanical wave, depends on those properties. So the speed of sound in air has a very low density, but it has low stiffness. But you still get pretty good speed of sound, roughly 340 plus meters per second at room temperature. That's over 750 miles an hour. But the speed of sound waves, mechanical waves, and a frequency that we can hear is greater. For the same temperature, water has 740 times the density. That means there's a lot more molecules. When that disturbance propagates, they got to rock back and forth. However, the stiffness of the air, much greater than a factor of 740. I slap the air, it goes down as far as I want. I slap the water, very little give. So the speed of sound is much greater in water. But the speed of sound in a solid metal like steel is even greater. It's got 8.5 times the density, so there's more resistance. There's more molecules to rock back and forth when the wave goes through. But steel is much more than 8.5 times stiffer than water. You hit the air, nothing happens. You hit the water, you get some resistance, it gives. You hit the steel, your hand gives. And that's why the speed of sound is greater. My geology friend here who's filming me likes to say that certain rocks are denser than other rocks, and that would slow down the speed of seismic waves. However, in general, when things get denser, they get stiffer at a greater rate than their density increases, thus those seismic waves increase in speed. Now, if we look right over here, cutting across the camera again because this is amateur hour, scientists and engineers have come up with this formula, which will be our theoretical equation. Our experimental one is velocity is frequency times wavelength. The stiffness of the air doesn't change whether we're doing this experiment at 20 degrees Celsius or even 30. However, the density of air does. Hot air expands. And so for normal air, which doesn't have a lot of moisture in it, like it's raining or you're not near some chemical plant, this formula has been verified to be insanely accurate. So if we measure the temperature in Celsius, we can plug it in here and figure out what the velocity should be in meters per second. We're going to compare this theoretical relationship with what we get experimentally by the frequency times the experimental wavelength. We're not going to see the air molecules moving back and forth. We're not going to see that wavelength, but we can calculate it indirectly from something called standing wave resonance. We're going to hear a precipitous rise in volume. And then we're going to measure things that will allow us to infer the wavelength. All right, so here comes some of the nasty abstract stuff. It's in your book for those in Physics 100. Physics 101, just do the best you can. Here's a picture. This is symbolically supposed to represent what's in the tube over here. This is the water level, which is the bottom of the column, and this is the top. This is the length of the air column. We're going to vary it as we go down. This first picture up here shows where the first resonance occurs. A precipitous rise in volume. And we're going to measure the distance from the water level to the top of the air. The theory should say it's a quarter wavelength. Then we're going to listen for a second one. Here it's a lot longer from the top down to the water, and the third one. When the smoke clears, the difference between the height of the air column between the first loud noise and the third loud noise is a wavelength. And that's how we get it. Now, what is this resonance we talk about? That's a big word. What is a standing wave? A standing wave is energy or disturbance that isn't free to continue out. The fact that you can hear me now if I back turn means sound can go in all directions and bounce back off the wall. Can you hear me? 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 Not much difference. And so in a standing wave, you got a wave going one way, but now it hits a boundary. Let's say a stiff boundary. And we want some of the energy bounces back, and it continues. But to have the energy remain, every time it hits the boundary, we don't want it to lose any energy. And so for hitting a hard boundary, like air going into the wall, or air molecules going into the water, we want to hit it neutrally, and it bounces back. And that's a condition that tells you how far away it is. But we have a soft boundary, because at the top of the tube, we have air to air. And things don't usually bounce back from hitting a soft boundary. It makes no sense. But here's the trick. I'm a moving target, hard to film. At the maximum amplitude, this thing stops and makes a U-turn every time. And so if we look over here at the wave thing, the air molecules are stretching out, they're stretching out, they're stretching out. And then at this point here, then they start to compress. And so if we put the air boundary here, it will bounce back. And that's what they're trying to show, which is not always clear unless you take some physics, right over there. But the bottom line is, we're going to listen for 3 loud noises. They're not going to be perfect. This is a hard boundary. This is not a perfectly soft, but the difference between them will be. So we're going to move this water level up and down and vary this height. First resonance, second, third. We're going to record where they are in meters. There's sample data here that we'll get to use. And from that, you can calculate, these are the positions of the 3 resonances. You can calculate the wavelength, because it's the difference between the third and the first. The length of the air at the third one, the length of the air column in that one, that's the wavelength. So now, My assistant is going to put down the camera and we're going to try and get these things. Don't try this at home. Okay. I'll let you see these numbers. And you can also see the board where they should be, right? So you can get over there if you want. That way you can control this. Oh. See the numbers and see the board. Does this work for you? Okay, perfect. And this thing's kind of crooked. Let's see if we can stiffen it up. All right. So my esteemed colleague and chairman is going to adjust this thing upward, and you should hear a precipitous rise in volume. In this case, it's going to occur close to 7.1 centimeters or 0.071 meters. There you go. So let's give the old community college a try. I think we'll drop it down a little slower. Give the old community college try. Just get it down to like there, then we'll go really slow. I know it's hard. Remember, it's a centimeter is pretty small. You only got to drop it a centimeter. Think of like a quarter of an inch or so. All right, that's a nice slow pace. Keep going like that. We're at 6. Keep going. Keep going. We're zooming in on it. Patient video watchers. All right, just like that. It's perfect. You heard that. Don't lie to me. All right, we'll go to our next one. Get down to like 23. So you can go from 23 to 24 or so. And so we would take our time, zoom in, and we'd find that to the nearest millimeter. Or in some cases, nearest half a millimeter. Our ears and eyes are pretty good. So the second resonance. It won't be exactly as loud. Question for the class, why? Well, Dr. Goldstein, it has a longer distance to travel, and when some of the waves hit the plastic, it's not perfectly elastic, it will absorb it. That's right, Poindexter, but it will still be pretty loud. Thank you. All right, here we go, we're getting close. Can you see this? Yep. All right. We want 23.7, so. I think we heard that. Did you hear that? And it was a little bit softer. Would you agree? All right, we'll try the third one. It's 40.6, roughly. And normally we would take our time. If it was a real lab, we'd zoom up and down several times. Everyone agreed. Have multiple sets of hands, just the two of us. And by having 3 values, if one of them is off, it's the difference. It will be pretty accurate. You get well under 1%. You can't see the wavelength, but you can hear it when it's right. We'll get the correct speed of sound. Where are we at? We're at 36, 36 and a half, 37, 37. Anticipation is killing you. I know you are. Don't change the channel. Okay, that's a good pace. Coming up on 39. Here we go. Go up the other way, please. You passed it.
Let's go down again. We passed it.
40.6. Yeah, yeah. Pain to move that thing. You get it? Mm-hmm. Okay, go up again a little slower. Did I miss it?
Yep.
There it is. So you can see by the third time it's not as sharp. there's more distance to travel, and some of those vibrations vibrate the plastic. It's not infinitely hard, so as you keep going and going, it gets worse and worse, but there's still 3 of them, and you'll get great data. Why? Because I did it for you. Goldstein out.